Hello and welcome to another IBM Developer Meetup for Australia and New Zealand. Thanks for geeking out with us. Be sure to like and subscribe to get the latest updates, news, events, and more.
Hello all, welcome to this special edition IBM Developer Meetup of AI in Health. Awesome to be here with you. I'm joined here with developer Steve.
Hello.
And his lovely country background. Looking good there, Steve. Again, thank you all for being here. I'd firstly like to begin by acknowledging the traditional owners of the lands on which we meet today, and I'd also like to pay my respects to elders past and present. So welcome. The agenda for tonight is we've done some networking. We've got an opening by the awesome Annette Hicks. Our first speaker will be Ivan Chua from the University of Sydney, talking about how he integrated AI into an app helping people to connect with the NDIS. Our second speaker is the awesome Nathalie Williems, who works at the IBM Research Labs on a cool AI topic that she'll and then we'll have a closing with some thank you for agreeing to the code of conduct when you came in today. Mostly just be excellent to each other, which I'm sure you all will be. Inclusive, diverse, respectful, and friendly, as we all are. So I just wanted to highlight, before we get started with Annette Hicks's amazing opening, a couple of AI and health projects that IBM's been involved in. So the first one is Simon, which is about combating loneliness in space with AI. So Simon, which is short for Crew Interactive Mobile Companion, choose your letters out of that.
I love this one.
Yeah, it's a very cool, and I mean, maybe you could tell us more about it, Steve.
It's literally, and to do that, I'm going to go to the International Space Station. I just love this scene and it messes with everyone's head. I'm not really upside down because there's no upside down in space, but yeah, it's literally like a floating assistant in space. So it jets itself around the cabin. Really cool YouTube clip. If you just search on YouTube, but yeah, it jets itself around the cabin. It helps the astronauts in space. Like, it's so cool. I kind of want one.
It is. It's pretty cool. And yeah, there is a YouTube video on that. I'll send these slides out after this event tonight, so you guys can peruse them at your own leisure. We've also been involved in helping build a new chemistry lab it combines AI models, cloud computing platform, and robots to help scientists design and synthesize new molecules while working from home. So it's an online lab platform, which is also pretty cool. And now I'm going to go to the opening. So to open for us tonight, we've got Annette Hicks. She's been with IBM since 2008, and focused on driving IBM healthcare solutions across ANZ. And she's got a strong appreciation for the value of AI in the healthcare industry, as she's previously been a healthcare professional. So Annette, would you like to turn on your mic and camera? And we'd love to hear what you have to say tonight.
And big round of virtual applause.
Yay! And do we have her as a speaker? Steve.
Oh, I missed that bit. Hang on a
Sorry.
second.
Annette, maybe try again now. Our apologies for that.
Thank you very much.
Tech glitches there. Thank you.
There we go.
Can you hear me
Annette.
now? Thank you very much. Thank you, everybody. It's very exciting doing it this way. It's really unusual, as I said to Steve. I'm normally presenting in live in a crowd, which I love because my healthcare background has made me appreciate what it's like for human contact. And I'm excited to be the pre-speaker before Ivan and Nathalie because they've got some very good projects to talk about. But as a health professional, I've been always very excited about AI and healthcare because I think it will help us advance forward in making sure that we can deliver better healthcare. So I focus at the clinical end. I've just finished 5 years working in Asia Pacific, assisting clients implement our oncology solution, which is an AI solution, which actually started to make me really appreciate where AI is extremely valuable, but there's also a lot of pushback from the industry. So let's just set the scene now, because healthcare is a very, conservative industry. And a lot of people see healthcare as being expensive. There's major issues with patients having the power because they don't have information. And one of the areas that I think is the area that AI has its biggest could have its biggest impact is in the area of big data, because there's lots of data and limited insights. And some of the things that we see in healthcare that's really pushing us forward is that since the introduction of electronic medical records and all sorts of clinical systems, we've got explosion of data. We've also got a lot of unstructured data where it's not visible to clinicians, because most of the time we're just looking at structured data, and this is where potentially tools like AI can help. And then on the flip side, there's a major gap. 45% of medical treatments are not evidence-based, and that takes up to 17 years for us to actually translate what we know about evidence-based medicine into practice. So we've got some really big challenges. And this is where I think AI can move forward and help us, because it can help us deliver those insights. So some of the things that we've been able to do in healthcare is we have been able to push forward with solutions such as the oncology solution IBM's had, but there's other players which we'll hear about today that have got solutions in the market. We've looked at advancements in medical imaging, which I think is the area where AI will probably start being our first real sort of breakthrough and become much more routine and accepted. And obviously in personalised medicine, we've seen the genomics, and because of the data impost with genomics, AI becomes an essential element. I just want to pause for a moment though, because when I said healthcare is very conservative, one of the things that I've found in my experience in presenting AI solutions to clinicians and other health professionals is there's a lot of pushback, because they have seen AI as something coming in and replacing them. But we need to start thinking in terms of augmentation and how does it underpin our industry to make better decisions, to give them insights they don't have today, and to also help them make breakthrough discoveries. Because I think that's where AI will help us improve what is helping in what's happening in our healthcare systems. I actually just want to end by looking at, I looked at a piece of research done by Accenture, and they looked at the top 10 AI applications by 2026. And the areas that they saw that would be the top players is automated image diagnostics and preliminary diagnosis. But I also see areas such as clinical trials participant identification, which IBM's already moved into, management of medications and connected medicine, plus some virtual type assistant capability. So we can see that there's a push into the industry. And I expect that as we understand AI better and how it might help the healthcare industry, I think we'll see a change in that dynamic of where AI will become part of our industry. So I'd like to thank everybody, and I'm looking forward to both Ivan and Nathalie's presentation because it's so exciting to see the work that we could do in healthcare and AI. Thank you very much.
Amazing, thank you.
Yep. Couldn't agree more. Thank you so much for joining us, Annette, with your insights into the future of AI and well. Coming up, and he's already on stage with us, so I will present him. Yeah, Ivan Chua is a technology professional entrepreneur at the University of Sydney. I've known Ivan and used to work with him for a while now, and he is a great speaker as well as always being really interested in everything he does, and he does it 200%. So he's got years of experience in leading teams of engineers and researchers in development and commercialization of robotics, AI, web, mobile. And I know he's also got a big community impact. So he is here to talk to us about building a custom AI search with Watson Discovery for the NDIS. So discussing, yep, go ahead, Ivan.
Oh no, I was just going to say quickly, just a bit before Ivan goes on, if anyone has any questions or stuff they want to ask, there's a Q&A section, and then also in general chat, we'll be keeping an eye out as well. So if there's any questions for Annette, want to reach out, say hi, please drop it in there. And then when Ivan comes up, which he's about to, also drop in some stuff. And
that reminds me as well, we'll be giving out delivery vouchers throughout this session. So to good questions as well, not just any questions. And we'll give out one to everyone that's been here tonight as well. So thank you for joining us. And Ivan, take it away.
Thank you very much, Developer Ali and Steve. Very great to be here today. Thank you for the invitation. As Ali mentioned, I worked with her previously for a brief period. So today, before I get started, I just want to mention that I prefer an interactive sort of presentation. So feel free to chuck any questions in the chat or Q&A, and rather than it being a one-way sort of presentation. Today, I'll be speaking about, sorry, actually, let me share my screen first. Can you let me know if you can see the full screen? Because I want to make sure that I'm sharing the right screen.
We can, Ivan, looking good.
Okay, excellent, thank you. Today, I will be speaking about applying artificial intelligence to the disability sector, specifically the National Disability Insurance Scheme in Australia, and how you can do that with IBM Watson. So to start with, just to introduce myself, I'm a technology professional and also entrepreneur at heart. I have 3 jobs, actually. Don't know how I'm surviving that. The first one being a business development manager at the New South Wales Smart Sensing Network, commissioned by the Office of the Chief Scientist here in New South Wales. So over there, we work from medtech to space and aviation, nano satellites, on the sensing aspects of it. So smart sensing basically means you have the sensor as well as the data side of things. So that's typically either the edge processing all the way to the processing of the data. So AI basically the software side. So that's for the New South Wales Smart Sensing Network. We represent 8 universities, and what we do is we set up collaborative research project between university, government, and industry. If you live in New South Wales, you probably would be using water, in which we have sensors attached to with Sydney Water to detect pipe leakage. And then separately, there are other projects as well with recently with the government tender for the Office of National Intelligence for a surveillance satellite. And then separately to that, I work with the Physicist of the Year, Professor Benjamin Eggleton at the University of Sydney in microwave photonics, and there I work a lot on defense applications, on microwave photonics in defense. And then separately to that, at the Faculty of Engineering and IT, I'm a lecturer in the undergraduate and graduate courses in computer science, teaching how many? 300 students actually both 300 students in postgraduate and 300 students in undergraduate in the topic of applying various emerging technologies in industry. So today I will be speaking specifically about one of them, which is simple. And this is basically the application of AI in disability. As for the other 2, I can very briefly mention that Motivable.com really came out of this COVID-19 period, in which me as a lecturer had a lot of problems delivering lectures at the university. And so it's an ed tech company that came out of that experience, and also from a personal experience of helping students with transition to industry. Bond Health is a medical imaging company in which we are currently working with the Royal Australian College of Surgeons with their education and examination processes. To date, we have graduated 95 surgeons for the past 3 years, I believe. And so that includes applying AI in healthcare as well. But today, I will be focusing on simple. So to start off with, now, although I love technology, I believe that it's not about the technology itself, but rather about the people, about the problem. At the end of the day, it's not just about writing code for the sake of writing code, but for a purpose. And for me, I'm always focused on that social impact side of things. If there is no social impact associated with something, I tend not to engage in it too much. And that's primarily because of my background. I'm from an area, an island called Borneo in Malaysia. So unlike what you may see in the internet, of Kuala Lumpur, the Twin Towers, I don't come from that side. That's the rich area of Malaysia, even though it's still a developing country. I come from the poorest state in Malaysia. I'm born and also I lived there for 15 years before I migrated to Australia because my little brother has a disability. So over there, 35% of the population live in poverty. You can see this. This is actually an image taken from my bedroom. You can see coconut trees and banana trees, as well as mountains in the background. People built their own houses there with wood and various materials they find everywhere. So through that experience, I've been able to see through firstly people that are on the receiving end of all of these new technologies. And that was very important because later on in my life, when I had the chance to come to Australia and also to study in the US, work in Hong Kong, Malaysia, it has been able to be my guiding principle in the sense that the work that I engage in needs to have that impact at this other side of it. When I was very small, we had an American group, I believe they were pastors that came over and held a leadership camp for us. And it was life-changing for myself. And so ever since I've moved to Australia since I was 15 years old, I've been able to understand that relationship between the actions that I take and the potential impact that it has on the people on an individual level. The reason we migrated to Australia was because my little brother has a disability. Since we were very young, my parents didn't know he had a disability. It wasn't until after he had failed many classes, had been beaten by teachers, scolded by teachers. There was even one instance when a teacher called him, labeled him, and shouted at him, called him stupid in front of his whole class, in front of his peers and friends. And through that experience, my parents was of the opinion that we couldn't stay back over there because my brother wouldn't be able to receive an education. He had been expelled, I believe, 4 or 5 times. I lost count of it. And every time he gets expelled, I would also move with him to a point where we literally did not have a school to go to anymore because, as I mentioned, we come from a very small place and there weren't too many schools. So from there, in 2005, we moved to Australia when I was 15 years old. Actually 11 years old, sorry. And ever since then, my brother has been able to receive the education that he needs in a special school and later on in the mainstream community. And I'm very proud to mention that despite being called stupid, he has successfully graduated from university, from RMIT in Melbourne. And so this is the impact that we see that Australia's programs has on people at an individual level. For me, I have a sense of responsibility that we have been able to benefit from this. And so now it is my responsibility to make sure that the transition to the National Disability Insurance Scheme works well and that I have a role to play in it. Separately, I have a cousin as well. He has cerebral palsy. I went back to visit him in 2008. So he's not able to walk independently. He's in a pram, and he's in a pram because his family cannot afford a wheelchair, and hence that's why he's in a pram. And my cousin does not go to school. He is not able to go to school because teachers, the principal, cannot accommodate to his needs, and so he's homeschooled. And I think that this has been the pivoting point for me because through that personal experience, I've been able to see how a bright person who has so much potential has not been able to access any opportunities because of their disability. Now, the reason I'm sharing these stories is because it's not about the technology itself, but rather the people that it affects. At the end of the day, we build new technologies because it has a positive impact on a person. And for my cousin, he was not able to go to school, not even be able to go to the bathroom himself. Apologies for this if this is a little bit too graphic. He would sit at the computer, in front of the computer for the whole day, because both of his parents have to work full-time and multiple jobs just to be able to pay for his therapy. And so as such, he's not able to go to the bathroom. So he has a bottle beside his desk in which he would relieve himself into the bottle rather than going to the bathroom. Now, so this is a view of how a person with disability lives, especially in a developing country. So with my cousin, his name's Jensen, I decided that as a lecturer, I'm teaching at the leading university in Australia. Why don't I do something? Sure, I'm not able to change the whole industry at once with many thousands of people with disability, but I thought that I wanted to start with one person. So impact begins with one person. With my cousin, his parents has been very concerned about his future, thinking about if they were gone one day, they grow old and they are gone one day, who's going to care for their son? How is his son going to find a job without education and with disability as well, with the limitations that come with that? And as such, I through many conversations with my cousin, I've been able to find out what his strengths and passions are, and one of which is coding, writing code. Not really writing code, it's more about logic. He loves logic. And so from there, I spoke with his parents and said, why don't Jensen learn coding? Because as an engineer, if you're a software engineer, it's not necessary to be in person, to be working at an office in person. You can work remotely. And so as such, from there, we started with C++. He worked very hard. He didn't have anything else to do anyway, because he would sit on the chair, for the whole day, otherwise playing games. You can see there's a notification on Steam at the moment on this screenshot. So once or twice every week, I would write code with him, and after 2 months, he has been able to learn C++ in terms of the basic, the logic, the basic logic and stuff. And then from there, we moved on to what is it called again? Unity to build the game. So now, when I went back to Malaysia to meet him, there was this one point where we were at a cafe drinking hot chocolate and having cake, and I asked him, if you had a superpower, what would you wish for? And he said, I wish I could move very fast. And I asked him, why is that? And he said, it's because that way I can go to parties and make friends. And so that killed me. He doesn't have any friends, and he's not able to make friends because of his mobility limitations. And so from there, I thought, why don't we make a game, since he loves Formula One as well, of racing, so that you can move around, you can even configure how you want to move around. And so from there, we were able to build a racing game in which he was a little bit silly with acceleration and, top velocity and all of those stuff. As you can see here, 10,000 units for the top speed. But from there, he was able to build that game successfully. So it starts with the people. At the end of the day, healthcare, do you define that by the offering, or do you define by the needs of a person? Because for me, I focus on the person. A person with disability does not only require therapy or certain surgeries from a medical point of view, but there are also other aspects as well. Moral support, education, career, and other aspects. And so that's where I started. And so as you can see, this is from an educational point of view, naturally, as I'm a lecturer. But from there, I thought to myself, I've been able to somewhat change my cousin's trajectory in life. Why can't I do something more? And to scale that impact, the best tool is technology. I have a vision, and that is a vision without barriers for people like my cousin, like my little brother. So from there, we've been able to think about what our purpose is, and we've decided that we want to be on a mission to empower the 1 billion people worldwide who live with a disability and to be able to lead their own lives. At the end of the day, it's about choice and control. It's about giving that choice and that control to the person to make their own decision, to be empowered to make that decision. Now, you might be thinking 1 billion people. There is 1 billion people in the world with disability, and that's by, that was by the World Health Organization or the World Bank, I believe. And the reason for that is because disability is not just restricted to people below 60 years old, but also people above 60 years old. As a matter of fact, aged care is very much driven by elderly people with disability. So as such, there's 1 billion people worldwide. Okay, I think I need to go a little bit faster. So from there, this is how it looks like in terms of the distribution of people with disability, specifically, 60 years or older. And so for us, we looked at the National Disability Insurance specifically. It was launched in 2013 with a pilot program. And then from there, they have been, I believe, in a pilot program till 2016, and from 2016 it was in a scale up sort of phase, and altogether we have $22 billion in total funding, and that is funded through an increase in Medicare levy, and also I believe some other sources. It was state and Commonwealth federal level. But in terms of the actual funding that goes to people with disability, that's $19.2 billion for a total of 460,000 people. So as you can see, it's a massive program. To give you an example, there are two other programs that we can compare it to. The first one is Medicare, obviously. I believe that's around 28 billion. So if you think about it, NDI is 22 billion, Medicare, 28 billion. And then you have the pharmaceutical benefits, PBS, the pharmaceutical benefits scheme. And that's, I believe, below $22 billion. So the NDIS is massive. If you have not heard about it, you will hear about it in the future. For every, I believe that there was, someone did some network analysis and say that, made the statement that what you would know someone who's in the NDIS by 2030 or so. So what is the problem here? And as I mentioned, people-centered. Start with the people, start with the problem. It's about solving the problem rather than just building software. In this particular case, for people with disability, there were three biggest problems. The first one is $2.8 billion was unspent. What does this mean? This means that a person has received $10 or $100 and did not spend $36 of that. 36% of what they received was not spent. And you might be wondering, why is this the case? This is crazy. If they have received funding, why wouldn't they spend every cent of it? And the reason for that is because, one, they could not find the right support to spend money on. And number two, a lot of people didn't even know how to get started in the first place. Secondly, it takes more than 3 months to find support. 24% of plans take more than 3 months to activate. Activate meaning spending the first dollar of money in the plan. The plan is a sum of funding that they receive in different categories, what we call support categories. Thirdly, 77% of people with disability want more choice and control. Choice and control is the underlying motivation for the NDIS. So how it worked was, the previous model is called the block funding model, in which the providers receive the funding, and you as a person with disability, you have to find the provider that has the funding. But rather, with the consumer-directed care in the NDIS, the funding, rather than being given to providers, it's given to people with disabilities. And then they go out to find registered providers. So 77% want more choice and control, meaning that the NDIS wasn't really working. And then on the flip side, you have the registered providers. 57% of them have not earned any revenue. That means a single dollar. Out of the 17,000 providers, registered providers, 10,200 of them have not earned any revenue. And that's because they couldn't find clients. Just imagine yourself paying $5,000 for registration, possibly up to $10,000. You receive, after a lot of paperwork, you receive your registration about 6 months later, 6 or 9 months later. And so you're looking at the letter, you're thinking, okay, now what? What's the next step? Okay, I need to find clients. How do I find clients? There's no way. You look out there, who do you know, who's in the NDIS and who's not, who has funding and has the right funding in the right support category. So that was the problem there. There was a mismatch in the market between people with disability and registered providers. And so basically the solution for that is you need to connect them. And how we decided to do that in terms of a solution is basically a search engine in which you're able to go onto the platform, type in, say, psychologist for a child with autism, or say a physiotherapist for a person with cerebral palsy, or you can even type the support category in which you receive funding in and explore what areas can you spend the funds on. And so that was the whole inspiration behind our product. And so this is just a view of the search page, and this is a view of the registered providers that you can find, based on unstructured text, or you can say full text search. And so how does it actually work? You have certain funding, you want to find support, you go on there, you type what you want to find, you get a search result, and then you can start calling them to find out which one may be the best fit for you. Okay, I'm not going to go through this. We don't have too much time. So how is it possible? How is it possible to deliver a search platform? Just to make it very clear, this is not a Boolean search. A Boolean search cannot work for this solution. Rather, it's more of a contextual search. And to be able to do search, the unstructured data needs to be structured so that you can do search on top of that. And in order to do that, what you have to do is build a knowledge graph out of the unstructured data. And so how does it work, a knowledge graph? Basically, you have nodes and then you have edges. A node is a circle, an edge is a line. And it can be bidirectional as well, meaning that the direction matters. Alternatively, you can have a graph in which the direction doesn't matter. And in this particular case, you can see that we have 4 entities. So each node is an entity. And then the line that you see is an edge, and that infers the relationship. In this particular case, we can see that it's bidirectional. So over here, you can see different types of data. You have a person, Bob, Mona Lisa, Leonardo da Vinci, and then you have dates, 14 July 1990. I think that's it. Only 2 types of entities, quite simple. But when you in practice, when you try to apply that and build a knowledge graph of the disability sector, it becomes very complicated. In our particular case, we did it for 17,000 providers, so actually all registered providers in the NDIS, and that comprised of 31.8 million nodes, not 31.8 nodes, 31.8 million nodes, and 84 million relationships. And so how do you build a knowledge graph? To be able to build a knowledge graph, you need to be able to identify in an unstructured text that Mona Lisa is a painting, Bob is a name, and that the other text around that word is not relevant to that entity. And so, in short, what we need is an entity recognition system, and that's where the AI comes in. So AI is used to be able to identify the specific text in an unstructured corpus in a big volume of text to identify what those words mean and to be able to classify them and understand the relationship between the different entities. So how we did that, what we had to do is firstly to annotate and to develop our training data, to prepare our training data first so that we can train our model and develop that final model in which we apply it to identify the specific entities and relationships. the traditional way of doing it is very, very somewhat difficult, and also a little bit tedious as well. And sorry, and the main reason for that is because the person that's annotating it may not be a developer or have technical background, and a person that has the technical background may not have that industry knowledge to be able to classify and annotate certain things. And so that's where IBM Watson came really useful. We use IBM Watson to be able to annotate the many data that we have to build our entity recognition model. And so how it works is you have your corpus, and then you annotate it using IBM Watson, in which there's a very easy to use sort of user interface. You train the model, and then you apply it to new documents. And so this is how it looks like. The UX, amazing, very simple. And that's how it looks like in terms of structuring unstructured text. And so it has been amazing using IBM Watson. Our platform, our business model, our solution would not have been possible without IBM Watson. Actually, it would have. I think that we would have needed a few more $1 million to be able to build it. So this is how our traffic looks like. And this was back in the day, I can't remember when. But yeah, Sydney being one, the first one. People loved it, absolutely loved it from the disability industry. They don't understand tech, but all they need to know is to go onto a platform and to type what they need to search. The technology takes care of the other stuff. And then on the provider side as well, they've been able to find clients because of our platform. So we've worked with many amazing disability organizations. It's quite funny, actually, because even the government itself did not use the solution that they built themselves, but rather they used ours. So I thought that was quite funny. And it would not have been possible without many of the partners which we had. IBM Watson for the annotation. We were part of the Google Cloud for startups, mainly because we didn't have a lot of money. And so basically anyone who could offers a little bit of credit, we went with them. We were very easy to bribe them. Sorry, I'm just looking at the chat. So Neo4j is the graph segment, is on the marketing data, and then we were part of several other accelerator programs. So yeah, so that's the end of it. Right now, a lot of my focus has been on the first two, and the main reason for that is because we had actually ran out of funding for Simple, and the server was very, very expensive to maintain, and without a revenue model. Without a sustainable revenue model, we found it very difficult to keep it up and running. We still do have the source code and the data, but it's currently offline, and that's because we don't have the money to run it continuously. So yeah, so that's basically what we do, and these are the two quick things, that we are working on right now. The second one will be relevant for this talk, and that's with the Royal Australian College of Surgeons, in which we provide the platform for doctors to learn and to undertake exams, so that they can become a surgeon. That's it. Thank you very much for your time. And I will have a look at the chat. I know that there's a lot of messages here.
That was amazing. Thank you for sharing that. And like totally could resonate with the whole tech for good side of things. Like, Ellie?
I think I might be lagging a little bit. Am I?
Tiny bit. No one noticed. It's
okay.
Fine.
I just wanted.
You go, Ellie.
I just to say that. Sharing that personal story with Ivan. That's amazing. We do have a few questions in the Q&A. I'm going to let Steve handle that though, because it seems like I'm lagging. Thanks, Steve.
Your internet was doing so good. We did discuss that this could be a problem, but I mean a feature.
Steve, do we have 2 minutes for any questions?
We sure do, and I actually have 2 questions that I was getting to as well, so I was going to ask them. But yeah, the whole tech for good stuff, like I love that. That's why I became a dev, like was to, as I always say to everyone, like use your tech superpowers for good, because that's what they're for, and this is totally that. My main question as a dev, and on that note, how can folks get involved? Like, is there a program to help teach like coding, like to get involved? Is there something that people can get involved with?
Yeah, so the reason the Australian community is investing so much money into people with disability, or 460,000 of them, is because the idea is to build their capacity so that they can find jobs and to enter the workforce. That way, they are delivering value to the economy rather than receiving money from the government. And so most definitely, employment is a big part of the NDIS, and many of them would benefit from learning how to code. But I think that perhaps right now may not be the right time. And the main reason is because it's so chaotic right now that I think they're still focusing on making sure that people don't fall through the cracks as opposed to, employment right now.
Amazing. And what have you seen as sort of as the biggest challenge so far, or what's the biggest hurdle that you've had to take on to sort of get involved with a lot of this stuff, like get a lot of this stuff running?
I think everything, actually, Steve. Everything. Starting out, you cannot do everything by yourself. So you need to find a partner, and a partner that you can trust, a partner that believes in your vision and your mission, and one that will go for that extra mile. So that was the first challenge. And then following that, it's about finding out what you want to do. And obviously start with the people first and the problem, and then developing a solution as part of that. So, that process went for a long time, actually. We adopt the customer development process, in which you form a hypothesis, you validate it, you invalidate it. And so we went in a circle for months and months and months. And this is where we landed with in terms of where to focus. And then from there, a lot of code to write. And also, sometimes cloud platforms can be a little bit expensive as well, depending on what you deploy. So that's a challenge as well. Every step is a challenge, I would say, especially in healthcare. As a matter of fact, I would say that software is a little bit easier. I worked on a medical robotics company spun out of the University of Sydney, and that was an invasive application. So had to go through all of the regulatory hurdles. So that definitely is 1,000 times harder, but even software by itself can be difficult.
Nice.
Yep.
Just going to read through some of the other questions before we wrap up first section. All right, what we got here? Aged care has been pushing patient-directed care for years with very poor results. How do you envisage this bridging the uneducated decider problem?
Uneducated decider problem. Right, very interesting. So I would say that it's about empowering them with the right information. And the right information comes from, a very large volume of data in which you need to be able to identify the right information from that. I would say that the golden area would be building some sort of, QA engine for the NDIS or even healthcare. But I'm not the right person to build it. I don't have the right knowledge. If anyone here has expertise, go ahead. I think that would be the ultimate solution.
Sounds like a new open source project to me.
Yes, could be.
Sorry, just going to try and get through a couple more before we switch over.
Yep.
Have you thought about doing a reverse by assisting providers to have their services being put forward as options for clients?
So that's what we do. All 17,000 registered providers are listed on the platform. If you want to, rank at the top, in which it's very transparent anyway, it's sponsored, you can select certain keywords in which we use the centrality sort of algorithms. We bump them up basically based on the keywords. So yes, that's possible.
Cool. Ivan, in your search platform, can you talk about the type of algorithms that are used by IBM Watson? May not have time to go into it all in detail, but I don't know if
in a nutshell, it's all about the graph. And so it's about identifying important nodes. You have basic stuff like the PageRank algorithm. And then there are other things as well, such as identify clusters. So you have clustering and then also edge prediction as well. And a relationship may not be explicit, but you're able to infer you'll be able to infer a relationship based on the other relationships. So those are the three stuff.
Makes sense, and a great overview on a short space of time. Ivan, I'm curious to hear your thoughts on where you see AI in disability in 2021, as we near the end of a very challenging year. Yeah, what a year.
I think that it's not just for disability, it's for the whole healthcare. The product offering needs to be offered in a very consumer-centric manner, because a lot of people find it difficult to trust AI or technology in general. So I would say that be 100% patient-centric or consumer-centric if you want to see any adoption at all. It's not about the technology. They don't care about the technology. You know, I tried explaining the technology at the very start. No one cared about.
Nice. And sorry, just time for one more. Andrew Soul, who is going to speak at the very end of our meetup about an upcoming health hack. Do you have a problem you want to bring to Hack for Digital Healthcare, which is the Telstra Health Hackathon coming up, which we will talk about more at the end. But anyway, if you have a problem,
yes.
We would love you to be involved.
It's basically the same thing that we've been building on. I still see lots of scope for improvement.
Yeah, amazing. Thank you so much, Ivan, and thank you, Steve, for everyone can hear me on that.
Yeah, you're just lagging slightly. That's fine. It's all right. Sure. When you're ready, go. Thank you, Ivan.
Thank you so much. It looks like we have to again. So no, amazing speech though, and you're exactly the sort of person we want in AI and healthcare. Please, so and that's what it's all about at the end of the day, changing things for the better. Our next speaker is the awesome. Well, and as well. Our next speaker is the amazing Nathalie Williems, and so Nathalie Williems, I've also worked with her. I just get surrounded by. She's a research scientist in the Health AI team at IBM Research Australia here in. She holds a PhD in computer physics, so looking and software development and modeling. Passion for the beneficial impact tech can make. Is about some of the work she's been researching, talking about the window into your health. Model neurological neuromuscular diseases, and I got to, so really happy about that. Welcome, Nat. Thanks for coming.
Big round of applause.
Thank you very much.
Thank you so much.
Great. Thank you so much, Ali. I'm sharing my screen. I hope everybody can see it. I'm just working from my laptop today, so great. Thank you for the introduction, Ali. Thank you very much for inviting me to present on some of our research today. As Ali said, I'm part of the Health AI team at IBM Research. I'm a relatively recent joiner. I'm coming into my first year in the team, and it's a great team and a great place to work and to be a part of. So I don't know how many people are actually aware of the research capabilities within IBM globally. I certainly wasn't until I joined, so I thought I'd give a bit of an introduction on this to start with. So there's actually 12 research labs that IBM has around the world. This little picture on the right here, it's a little bit old, but it's still relevant in terms of the geographic locations. And it employs about 3,000 researchers that are all working on different aspects of research. And IBM, as some people might know, actually holds quite a strong track record of invention and innovation. And when I was doing a bit of research for my own position here, I was actually quite surprised to see how many sort of landmark inventions have come from IBM, like things like the hard disk drive, the ATM machine, the magnetic stripe on credit cards. And in terms of innovation, there's a strong drive in terms of patenting. And IBM, for the last 26 years, has held the most amount of patents granted in the US. So there's a strong focus on research, and all of our labs sort of contribute towards that trend of innovation. And so it's a really exciting place to work. And more recently, the sort of focus areas of this research has been around hybrid cloud, artificial intelligence, quantum computing, and science. So I'm part of this science sort of focus area. And there's a global initiative around healthcare and life sciences. There's a global sort of team. There's separate teams in the different locations, but we all sort of fall under that umbrella. And one of the core focuses of healthcare within this area is healthcare imaging, right? So we're looking at all types of imaging across the body. You can see some of these pictures here on the right. That we can image now in clinical settings, all kinds of parts of our body. And the aim of our initiative around analyzing these images is to help support clinicians and hospitals and doctors with screening, with disease diagnosis, with tracking and predicting disease progression. And some of the core methods that we're using to develop these solutions are all around computational modeling of these problems, right? And that includes AI-based technologies, and particularly deep learning technologies. And so what we do here in Australia is, well, we actually have a sort of a strong track record in terms of applying artificial intelligence to medical imaging. This slide is sort of like a published slide for all of our most recent publications within, particularly around developing and applying novel deep learning architectures to imaging and particularly eye imaging. And we also often present our work in some of the top conferences around medical imaging and in that space. And so this is a picture of, on the right is a picture of all of the members of my wonderful team. And yeah, it's a joy to be there. And so I thought I'd give you a little bit of an overview of a more recent initiative, sort of a strategic initiative that we're a part of here in Australia, in Melbourne. And we like to call it AI for the eye. Another way of framing that is to essentially use the eye as a window to your health, right? And so the core focus around this strategy is to model diseases that can be tracked non-invasively through the eye, right? And so this picture on the right that I'm showing, it's a little bit complicated, but essentially it tells the story of the motivation around using the eye as this window to your health, right? It turns out that several conditions, neurodegenerative conditions, cardiovascular conditions, and of course eye conditions actually present themselves in the retina. This includes things like stroke, Alzheimer's disease, Parkinson's disease. All of these diseases and conditions have ways of presenting themselves in the structures of the retina. The retina is at the back part of your eye, and it connects essentially the back of the eye with the brain, right? So there's a nerve connection between the brain and the eye, and therefore we're kind of using this eye as this window, right, into how the brain functions. And the reason we're interested in using this retinal imaging for tracking these conditions that are also neurodegenerative and sort of related to the brain is because retinal imaging is, number one, cheaper, and number two, it's much more patient friendly, right? So if we take Alzheimer's disease as an example, that's currently assessed on basis of a protein called amyloid beta. And the way that we assess the status of that protein within Alzheimer's patients is to either image them using a PET scanner, which is expensive and not all that common, or through invasive lumbar punctures, right, where we extract cerebral spinal fluid from the spine. These are costly procedures and they're highly invasive, right? So if we can develop technologies that can analyze how these diseases present in the retina using these much more, less invasive retinal imaging technologies, then we're on our way to a much better system essentially to help these patients along their journey, right? And so the central question that we're asking here is, can we develop technologies that detect these and sort of model these diseases also in terms of their progression, through the eye, right? And so what diseases are we actually focusing on most recently? We're looking at eye conditions like age-related macular degeneration, also looking at Alzheimer's disease, but today I'll be focusing on an eye condition called glaucoma. And what we're interested in doing there is to develop technologies for detection of glaucoma based on retinal imaging, and particularly have a focus on early detection of this condition. We also want to explore and understand the relationships between the structures of the retina and their function, how they actually affect our ability to see things. And then we also look at things like personalized medicine, where we're interested in developing models for forecasting how this disease progresses on a personalized basis, okay? And so I'll be talking through each one of those aspects throughout the rest of these slides. So firstly, I'll zoom out a little bit and talk a bit about what glaucoma actually is. So it's a neurodegenerative eye condition. It's one of the leading causes of blindness worldwide. There was an interesting meta-analysis study that was published 5 years ago that projected that about 80 million people would be affected by this condition by this year. And the way that it manifests and the way that it actually happens is through damage to the optic nerve, right? So here is an image of a healthy eye, and this is this retinal structure that I keep referring to, right? So it's at the back of the eye, and this optic nerve is essentially a bundle of fibers that connect the retina to your brain, okay? And in a normal eye, you have synthesis of fluid that happens at the front of the eye in the cornea, and in a glaucomatous eye, the usual drainage of this fluid through these canals in the eye is blocked, okay? And what happens then is that there's a certain amount of pressure that's exerted by this fluid at the front of the eye that basically traverses the rest of this vitreous body, and it causes this intraocular pressure to build up within the eye. And that exerts itself onto the retina and essentially starts to damage the optic nerve fibers as well as other structures in the retina, okay? And that results in, firstly, in the early stages of the disease, it results in peripheral vision loss. So you essentially have just tunnel vision. And then if it's undetected and untreated, eventually it affects central vision and causes total and irreversible blindness, right? So early detection is key with this particular condition. And any damage that is already caused by the condition before we identify it, that's already irreversible damage, okay? So again, early detection is key, and that's what we're really interested in trying to do. All right, so let's firstly understand how glaucoma is detected and how it's diagnosed. There's various vision-based methods of identifying this condition. There's visual field tests. This measures your peripheral vision. An example of this test is shown here. So essentially, a patient will come in and go through this test. It's a long and tedious process. There's also visual acuity tests. So that's this infamous sort of letter chart. Anyone who wears glasses will sort of recognize this. And then there's some other methods that essentially look at measurements, more like quantitative measurements of the eye, to try and establish a diagnosis for glaucoma, right? But the issue with these vision-based tests is that they're quite subjective. There's problems with reproducibility. So there's visit-to-visit variability in terms of estimating the visual field of a particular patient, as well as the fact that this is already looking at a later stage of the disease, right? We are trying to establish whether your visual field, the way your peripheral vision is affected or not. And if it is affected, then you're already at a later stage of the disease because that damage has already been done to that optic nerve, right? And so we want to start looking at other ways of assessing the progression of that condition, right? And these imaging-based methods are sort of coming into clinical practice more and more. And I'll go through to the two most common ones that are available at the moment. One is called fundus imaging. I'm showing you an example of that here. This is essentially an image of the entire retina. And a healthy eye looks like this. This is sort of the optic nerve head, right? So this is again where that nerve fiber bundle goes from the retina and into the brain. And what we can see with a glaucomatous eye is, again, because of this pressure buildup, we have damage to this nerve head, and we essentially get a cup that forms. And so you can really detect that within this fundus image as well. So it shows these features around the optic nerve head. And then we also have another imaging technique called optical coherence tomography. It's a bit of a mouthful, so I'm going to say OCT from now on. And this generates sort of 3D volumetric scans of the retina, and that incorporates depth, okay? So that's a really nice imaging technique that allows us to assess features of the retinal layers, right? The retina is composed of about 10 layers, and each one of those can undergo degrees of changes and damage throughout the glaucoma trajectory. And so what we're seeing here is the same cupping phenomenon, where obviously the optic nerve fibers have started to become damaged, and we can really see how that affects these retinal nerve fiber layers through this OCT image, right? These imaging technologies are more reproducible. They're becoming to be much more easy to measure and much more cost effective. And it will allow us to establish these structure-function relationships so that we can enable earlier detection of this condition, okay? And so that's really where we're trying to focus our efforts here. And so I wanted to just recap on what our task actually is in this context. Again, we want to focus on early detection because then we have a better chance of intervention. And there are treatments available for glaucoma, so it's a good thing to do. We want to establish these structure-function relationships so we can reduce our reliance on subjective testing methods and improve the clinical best practices. And we want to generate these personalized forecasts so that we can better manage our patients, particularly because the presentation of the condition can vary depending on the patient. Some can go through a rapid progression and deterioration in glaucoma, and some will have much slower trajectories. So we want to be able to tailor our treatment of these individuals based on these forecasts, okay? And so then again, the central question we have is how can we leverage these medical images and how can we derive quantitative markers for this condition, for this automated detection, characterization, and forecasting of this condition, right? And so those three aspects is what I'll focus on. Before I do that, I'm going to talk a little bit about a central theme to our approach in this space, and that's to use convolutional neural networks, right? So people in the AI space will know that these CNN networks, or these CN networks, have shown great performance in image recognition tasks as well as segmentation tasks. They're useful for a variety of reasons. They automatically learn abstract feature representations that are derived directly from your images. So unlike more traditional machine learning approaches that require specific features that are either handcrafted or measured in some way, we can actually learn directly on the input image. So we don't need to process this image necessarily for us to develop models using this approach, using a CNN approach, okay? They can learn translational invariance that's present in the images due to the convolutional nature of the architecture. And from a computational perspective, they're useful because they can reduce the dimensions and scale to large data sets, right? So that's again because of the convolutional nature. So I thought I'd give a little bit of an overview of how these actually work in case people may not be entirely aware of the technical details. It's actually kind of a simple approach. So let's say that we have an image here that's represented by the blue box, and we have what's called a kernel, right? A kernel is essentially an array of numbers that we apply to the image, and we essentially do the weighted sum of the kernel to the region of the image that the kernel is overlaid on. So again, we have our blue sort of box here, and we have our kernel, and that's the shaded region. And the smaller numbers in the right-hand corners are the numbers for the kernel, and the bigger numbers are the pixel values. Let's say that they're the pixel values. So if we multiply the small numbers with the big numbers and then added them up, we get the single output of this convolutional operation at this point in the image, right? And as we go, we slide the kernel across the image, and for each slide, for each sort of stride as it's called, we get a different output, and the total output is called the feature map, okay? And we repeat this process as much as we want with different kernels to essentially generate these abstract feature representations for our task, okay? Now, this can be applied to a three-dimensional image as well, and that's important when we're considering these OCT scans. They're 3D volumetric objects, so we need to be able to do this in a three-dimensional manner. And what I'm showing here is just a simplified representation of that, where let's assume that it's an image with 3 different color channels. So we have a 3-dimensional object now. We have our pixels for each particular channel. So we're looking at red, green, and blue. And we just have that within like sort of the third dimension. Let's imagine it's an NumPy array. The third dimension of those of that object is essentially the different color channels, right? And so we can apply the same convolutional operations in this 3-dimensional way. And this kind of forms the basis or the core of our approach to solving these tasks, okay? Now, let's get to the good stuff. So I'm going to talk a little bit about our approach to detection of glaucoma using these 3D OCT retinal scans, right? So the objective here is to accurately detect the presence of glaucoma using just these images as input, right? The traditional approach, and there's vast literature on this, is to derive features explicitly from the retinal images That involves calculating the thicknesses of the retinal layers and different features around the optic disc. And so that requires a certain degree of medical expertise or clinical expertise, as well as some labor in order to derive these features explicitly, right? And I just wanted to show another example of an OCT scan, so we again can visualize what this input actually looks like. And here we have a representation of the different retinal layers, right? So this is sort of what the input image is. We can derive these explicit features from these images, but it's labor intensive. And there's essentially a presupposition of what features we believe are important to predict glaucoma with this approach, okay? We try to compare that traditional approach with a purely image-based approach. So that's essentially our method, and that's what we were interested in investigating here. We wanted to see how a convolutional neural network based on just images performs in terms of glaucoma detection versus the more classical approach of using derived features and training classical ML algorithms on these extracted features, okay? And so I just wanted to spend a little bit of time on the actual architecture of the deep learning model that we applied in this study. This is a purely convolutional neural network. We don't have, if people are familiar, usually you would have a convolutional layer, a set of convolutional layers, and then some kind of pooling operation before you do your successive convolutional layers after that. Instead, here we have just purely convolutional layers. We have 5 of them, so it's a relatively simple architecture. It's not very deep. And what we have at the end is a global average pooling layer, and that enables us to visualize class activation maps, which I'll show you in the next slide. And the other thing to note here is that because it's purely convolutional, you can essentially train this on any size of image, any dimensional image that's an OCT scan. Okay, so we don't need prior information, and we don't actually correct for any laterality. That's essentially whether the image is coming from the left eye or the right eye. Often within these approaches, they align the eye so that if it's coming from, say, we want to just use images from the left eye, if it's an image from the right eye, we flip it, right? And that's that laterality correction. Again, that requires pre-processing, right? We want to know how this does on just the image without correcting for any of these other things. And that's why it's called a feature agnostic approach, right? Okay, so how does it perform, right? We train our models, we compare it to our traditional machine learning approaches, and what do we see, right? So this was a nice, pleasant result. What we see is that we actually get much better classification performance in terms of the area under the curve characteristic. And the CNN approach, right, performs the best compared to these other machine learning methods. And to go back to that class activation map method that I spoke about earlier, we can now actually visualize the regions of the image that the CNN is focusing on in order to make its glaucoma diagnosis, okay? And what we see is that the network learned features are actually similar to those that would usually be used by clinicians to diagnose this condition, right? What you see, that's what you see here, right? So essentially the regions where the network focuses on are shown in red. It's a heat map that's overlaid on the original image. And we have these on FOSS view, so that's essentially just like looking straight onto the retina. And then we have the side view where we can see the layers of the retina, right? So those are the 2 different categories here. And for a healthy eye, we see that there's features around the optic disc, but there's not really a big focus on the neuroretinal rim, as it's called, from the optic disc. And then the side, we can see that as well. We're not really focusing on the optic nerve head because this is a healthy individual, essentially here. We see that, right? If we look at an individual who has glaucoma, we can see how the network concentrates much more on this optic disc, which again is the most visible region of damage. And we can see, that it also focuses on features around the optic nerve head and those fiber layers as well. So that was a really nice output, and it's good to be able to, bring in some interpretation to the network, essentially, because, often a limitation of deep learning is that it's a black box approach. We actually have methods to enable interpretation of the predictions being made by the network now, and this is one of them, right? So it's quite nice to see. Okay, so this is glaucoma detection, and again, we're trying to focus on early detection here. The next step was to approach it from the structure-function relationship, right? Let's try to reduce the reliance on these on these highly variable vision-based methods of assessing this condition. And I'm not going to go through this in as much detail as the previous study because it sort of set the scene, but I'm happy to sort of answer more detailed questions on these. So here, the aim of the study is to try and estimate the visual function of an individual directly from the OCT scan, directly from this retinal image, okay? Because visual field tests are noisy and subjective and there's poor repeatability, we want to find a surrogate for this, right? And if we can understand how visual function is directly related by analyzing the structures that we can see in the OCT scans, then firstly, we have a better understanding of the biology of this disease, but also we could, again, potentially have a surrogate for these noisy visual field tests and instead look directly at the image to estimate an individual's visual function. Okay, so it's kind of exciting to be able to try and do that when we're just looking at OCT scans, right? So our method here is similar to the one I just spoke about. We have another convolutional neural network approach here. We have almost the exact same architecture for that CNN. So that's again why I wanted to spend some time on it. And what we're doing here is training two regional networks that are focused on different regions of the retina. One that's centered on the macula. This is just another term, and it's just another region in the retina. Okay, and that's responsible for different aspects of our vision. That's why it's important. And then we have our optic nerve head scans. So these are the same ones as what I was showing you before. And again, that focuses on that nerve fiber bundle. Okay, so we have two separate networks that we're training, and then we actually integrate the information that we're sort of deriving by constructing these abstract feature maps. And we have our output at the end of the output layer of the network, which is actually estimating the visual field index, right? So that's that showed you an image of that before. It's essentially, estimating what our peripheral vision is like. We want to estimate that directly from these scans, right? So what we can see here is that this combined approach of looking at both the macular region and the optic nerve head, essentially allows us to estimate this visual field functionality better. We have a slightly better performance here. And in this paper, there's a lot of analysis in terms of the errors and whether or not it's really that informative to incorporate these regions. But from a purely performance perspective, we still get a slightly better performance by combining them. And we can actually estimate this quite well, also from a historical perspective. So in this study, we had access to data from the same patient over multiple visits to the optometrist. And we can see how this visual field index essentially decreases as glaucoma progresses, right? And we can sort of map that trend pretty well, especially considering that we're only looking at information from a scan and trying to estimate this function directly from that. And so here I'm showing again sort of this application of class activation maps, and we're able to visualize the regions of the retina that actually contribute to these visual field test results, and we can see how these change over the course of the different visits. Okay. So that was our structure-function relationship work. And the last part is this personalized forecasting, right? So this study is, I almost feel bad just representing it in one slide because this study is quite comprehensive and it was a lot of work. So if you are really interested in this work, I would highly recommend reading this paper. But the objective here was essentially to generate personalized forecasts for improving the management of glaucoma patients, and essentially to forecast the changes of the structures of the retina as well as their function, right? So as well as the visual field function. So here we're kind of taking the last two studies and we're putting them together to create these forecasts, right? We're looking at whether or not glaucoma is present. We're looking at the retinal structures, and we're looking at the visual field indices as well in this big sort of data set that we have access to. And the aim here, or the approach that we took, is quite similar. Again, we wanted to compare how the classical ML approaches using derived features actually stack up to a CNN, right? A CNN that analyzes the images directly and generates these abstract feature maps, right? And in terms of the intricacies of the models, so what we have is we have a traditional machine learning approach, right? So we're kind of showing those results here already. that are based on, these are based on the measured features, right? So these are like derived from the scans manually. And then we have the same sort of feature vector, but without the derived features from the images. And instead, we actually append the abstracted features that are generated from the CNN. Okay, so you can imagine the feature vector that's usually input to a machine learning algorithm, and that we have feature vectors for different visits, right? So we take them from different visits and we use that information to forecast for the final visit. We can change the number of visits we include in our performance analysis. And rather than taking these measured features, then we take them away and we add in the abstracted features from the CNN, right? So we essentially take the last layer of the convolutional neural network and we append that to this feature vector, and then we see how it performs, right? And so what we can see is that the actual errors of this approach is less. It's less than when we take these measured features, right? So there's essentially kind of a backstory there that says that, well, maybe there's information in the OCT images that we're not capturing by focusing on just these purely derived features, right? This is that presupposition aspect that I was talking about earlier, right? So there could be things that we're not aware of that are important in assessing glaucoma that therefore we miss when we want to derive these features. And that might be captured by the CNN approach, given we give it the raw image itself, right? And again, we have very good performance here. We can see that the CNN-based, when we incorporate the CNN-derived features, there's a slight increase in performance from an R-squared perspective, but also from a mean absolute error perspective. And in terms of the number of visits that we include in this forecast, we can see that the lowest number of errors, we incorporate 3 visits to then forecast for the 4th, right? And so this way we can actually start assessing how rapidly glaucoma will progress depending on your historical manifestation of the disease, right? And so this is where that personalized aspect really comes in. Okay, I'm not sure I think I'm a little bit over time, so that's pretty much everything I wanted to do to say. This is sort of just a quick overview of some of the research that we're doing within the glaucoma space. And again, I have to thank the team. They're the ones that did all of this work. I'm just presenting it. And thanks very much for your attention. I'll happily answer any questions.
You turn your microphone on. That was amazing. Thank you.
Yeah, much, Nat. Really appreciate you being here tonight and sharing all that knowledge with you. I know there is a heap of questions in the Q&A. I'm going to let Steve present those, just in case my
we don't want to don't jinx it.
His bandwidth isn't holding up too well.
don't jinx it. We do have a whole bunch of questions though, so let's get annoyed with those. So what's the biggest challenge in detecting medical conditions via the eye? Is it getting enough scans, or is it getting enough good data from those scans?
Oh, well, it's a bit of both, to be honest. I mean, in the medical imaging space, we're not often dealing with very large data sets, right? So even in some of those results that I was presenting there, I think the largest data set that we had was about 600 patients. And so one of the most common problems in this space is to develop models that are generalizable based on the fact that, we have usually we have access to a limited data set, and that's to do with patient consent and data security and aspects like that. And so that's a challenge. And then, yes, the second challenge is, of course, well, now we have access to these images. What do we do with them, right? And so deriving good features from these data will be dependent on the quality of, say, the scanner or that particular visit in terms of the imaging, right? And so there are, even when we have our data set and say that's already constrained by the number of patients that we have, we then also have to sort of do some quality control on those images so that we can ensure that we can derive quality features from them. So we kind of have thresholds that we have to apply, and that means that we kind of, that sort of is part of that process as well. And so there's those two are really, it's actually a great question, because they do highlight sort of some of the limitations that we currently face in terms of developing this technology further within the medical imaging space. Yeah.
Amazing. Why couldn't you just use a model like Inception, Renotte, etc.?
Yeah, so that's there's a few papers out there that use sort of transfer learning approaches with existing architectures, but there's two reasons why we didn't go with that approach. The first is that we wanted to see how well a purely convolutional network will perform, and the reasons for that are also, well, and then, so we wanted to compare that to like other architectures, and we did that comparison to some of the studies, and it turns out that that the CNN, actually, like the fully convolutional network, does perform better. But there's more details in the paper. And the second reason is that we can then also use this sort of class activation map, right? So we can use that. Given that we have a fully convolutional architecture, we can map back the activations in the last layer to the original inputs, given that we're not using any sort of max or average pooling layers in between the convolutional layers. So that's why we went with that architecture.
Amazing. That makes sense. Side note, I did say to Ali not to jinx her internet, and here we are. Anyway.
Yeah, it just dropped off. I got a bit boring.
She'll be back. It's fine. Another question. I have a family history of a glaucoma, but I've always been told if they're regular eye checkups, it's very easy to detect early and treat. Is that correct?
Well, I mean, I can't really comment on that. I am not a medical expert, but I do know that, at least from my reading of the literature, that there's certainly still sort of challenges within this field in terms of early detection. But it kind of depends on the patient as well, right? And the reason that some of this early detection is problematic for some people is, for example, if they have myopia, right? So people with long long or short vision, I always forget which one it is, but essentially people like me, right? So I've got like -8.5. That is a confounding factor for the diagnosis of myopia, because it affects essentially the thickness of the retinal layers because of the deformation of the eyeball, right? And so it kind of depends on the patient, and that's, again, why it's relevant to sort of personalize medicine and diagnostics around the individual. But I cannot speak on on behalf of medical experts here.
Yeah, which is very solid advice. Can retina scans be done without the need of medical professionals? Can you do it yourself? That's the dream, right? Send off your own scans and get an AI doctor to assess.
That is an awesome question, and yes, you can. You can take. There's fundus cameras that you can attach to your phone, and they're relatively cheap. I think they're like $100 or something, and you can essentially use that camera, take a picture of it, and then you can send it or upload it to some server, send it to your doctor or your eye professional, and they can make this assessment for you, right? So that's the case for fundus imaging. OCT isn't there yet, but I know that there are developments in that space, and I think there are some prototypes of handheld OCT devices, and that's a fastly developing space. So yeah, it is possible.
Amazing. Cool. Presumably you'll need a number of images from the same patient to check deterioration, or are you just comparing against a norm?
Yeah, so for the forecasting models, you definitely need longitudinal data, right? So images collected from the same patient at different time points in order to develop these forecasting models. So I mean, yeah, I think that's necessary. Obviously, the more accurate we can get our predictions for the least amount of data. That's sort of that dream, right? This parsimonious model. That's the aim. But at the moment, as I showed in this last study, we kind of needed around 3 visits of patient data in order to make these forecasts as accurate as possible. So that's sort of where the limit lies at the moment.
Yep. How many of these AI disease detection have been operationalized, and how long did it take to train your CNN, and how much data did you need?
Okay, so for the first question, operationalized, I think there's some of this technology is being incorporated into some offerings by Watson Health. So there's some of this is underway, but most of the studies I was just showing are studies that were either published this year or the year before, and of course there's a degree of development to be done before this can actually be operationalized or commercialized. But there's tremendous interest in doing that. Second question was, how long did it take to train the CNNs?
Yeah, how much data?
How much data? So for the first study that I showed in terms of detecting glaucoma, that was on 1,110 scans. That was the total data set. And so obviously you split those. That was the total data set. And I think it took like a couple of days to train. I think we used GPUs to do it. But I'd have to check that. I didn't actually train these models, but yeah, I don't think it's I don't think it was a long, a very long process to train these models.
Sorry, just talking to Ali. All right, we might just ask one more. What are the pathways or options to commercialize these computer vision medical imaging models? Licensing of IP, go to market directly? ?
Yeah, it's great. That's a great question, right? So that's sort of the balance that we need to achieve still from IBM's perspective. Do we want to license this technology, and do we want to protect it, right? Like often that's the trajectory that we would go down. In fact, we've already released some patents this year on the basis of some of this technology, not that I showed here, but other variations of it. And yeah, I'd say that's sort of step one. We want to protect our IP, and then work together with the business units to sort of productionize these models, ensure that they perform in the way that we want, and then integrate that within existing offerings. Yeah.
Okay, we decided to ask the last 4 questions anyways. Now, this next word's a little bit tricky, and it is getting rather late, and I haven't had a coffee for a while. So, keratoconus. I'm probably saying that completely wrong. Anyway.
I think I'm looking at it.
Okay,
I had
that top one.
I had keratoconus for 5 years. The only surgery I could do at the time was cross-linking. Is that the right question?
Yes.
In the Q&A, Nat. Yep. Keratoconus is similar to glaucoma. Is there any real treatment for both keratoconus and glaucoma, rather than early protection or to delay or prevent the disease? And I'm back. Sorry, I've just moved to the new house, so apologies, everyone. Thanks, Steve. Thanks, Nat.
Yeah, so I can speak on the glaucoma part of this question. There are treatments for glaucoma. The emphasis in terms of early detection is purely to try and salvage and save as much vision, prevent as much vision loss as possible. And yeah, there are treatments to alleviate the pressure buildup in that usually occurs at the front part of the eye that then generates this interocular pressure. Yeah, so I think they exist. I would say talk to your doctor. I can't speak really on this other condition. I'm not very familiar with it. Sorry.
No, that's cool. Did you have a chance to look at the use of GANs to augment the training set?
Great question. Nope, we did not use GANs, but we did use augmentation. There were certain transformations essentially we applied to the images, and also basic operations like altering the brightness and contrast and things like that to try and expand our data set a bit more, but we didn't use GANs.
Okay, and last one, how are these features extracted from the retina scan correlated to ailments associated with other organs, i.e. overall health and cardiological issues?
Okay, great question. So I'm gonna move away from the glaucoma aspect here, because obviously we're looking at different conditions here. And so generally, features that we can extract from the retina in terms of like the layers and their thicknesses and their deterioration, as well as the other features that I was talking about around the optic disc and the macula and things like that. Other conditions present themselves with the same sort of structural changes, right? So that sort of goes back to that slide that I had about like stroke and Alzheimer's and things. All of those conditions also have effects on the retinal fibers and in the retina, right? The optic nerve fibers, and they result in thinning of these layers. So the structural features that we can derive from these scans quantitatively, like with manual effort, as well as using these CNN-based approaches, could potentially be applied to these other conditions as well. And we're actually also looking at incorporating other data, like genetic data, in order to help with the distinguishing aspects of these conditions, right? So like I was saying before, like myopia is kind of a confounding factor when you want to diagnose for glaucoma, and potentially if we could incorporate genetic predisposition for either one of these conditions within our models, then we can sort of refine our ability to distinguish between these different conditions using the same data set. So that's currently an active area of research that I personally am working on. So
Amazing.
Super exciting.
And we're big fans of the work that everyone does in research. Actually, and it's surprising, like some of the stuff that pops up. I was reading a news article the other day and I was like, wow, this is really, really cool. IBM research. So I'm going to share it because it's one I thought was
yeah, super relevant. I remember you sharing this with us, and I'm like, this is exactly.
And this is one of Japanese colleagues who basically built a suitcase to help for navigating. A robot suitcase that could replace canes and guide dogs for blind people, which is amazing. Uses a whole bunch of sensors to help them navigate obstacles and basically move around, which is really cool. Anyway, just want to say we love the work, love the talk, and thank you very much for spending time with us today.
No worries. Thank you so much.
Thanks, Nat, and thank you to Ivan as well. Thanks to both our speakers. You've been amazing. So many great questions from the audience as well. Just please check your private messages as well. I know our amazing colleague Gloria has been sending you through some delivery vouchers for those awesome questions. So